times don't see that. What we look for are a whole bunch of other things. One of those things are these little guys called tektites. And tektites are essentially little blobs of melted earth material. And as this melt flies through the air, it kind of gets rounded off, becomes a little more aerodynamic. And by the time it hits the ground, it's cooled into a solid piece. And they just kind of litter the landscape as part of this ejecta that's thrown out of the crater area. So some of it can be material from Earth, from the crater. Some of it might be material from the asteroid itself, although oftentimes those are pretty much vaporized. But whenever we find these little tektites, we know we've got ourselves an impact of some sort, whether it was comet or asteroid. So these little guys, you see this ballpoint pen here for scale, they're pretty small, but they can form for miles and miles away from the impact, covering huge areas with just little scattered blankets to fairly thick blankets, depending on how far away you are. The Sudbury impact in the Canadian Shield, this is basically just to the northeast of Lake Huron up in Canada. And that impact had debris that was ejected from there all the way across the Great Lakes, through Michigan, across the Upper Peninsula, and out into Minnesota. That's how far the splash went. And then that was the radius that draw a circle around. Huge impact back in the Precambrian. And we can still see some of this debris up in the Upper Peninsula. There's some great exposures up by Marquette. We take one of our classes there. And there's as much as 30 feet of debris from this impact, all the way in Marquette, 160 kilometers away from the impact. And we've been able to find these little tektites among some of that debris. Pretty amazing. So you're standing there, and first you feel the shock wave, and then the temperature and pressure increase to where you're basically toasted at that point. But then out of the sky comes a rain of debris that covers the area in 30 feet of junk, and that's your day. Man, I'm trying to escape that. And we see around the world a whole bunch of these impact sites. There are about 120 or so of them, and those are primarily all identified on land. And we know Earth is 71% covered in ocean, so we're only looking at maybe 30% of the impacts. I mean, they obviously hit out in the ocean too. We just don't have any evidence of that. You'll notice we do have a couple that are in areas where we see that evidence pretty much buried. And of course, Chicxulub here in the Yucatan is the one that they think ended the dinosaurs in the Cretaceous. So it happened. Now here's the remains of one, the Manicouagan meteorite impact up in Quebec, about 200 million years old. And what you're looking at isn't the big crater. It isn't the big ring system and all the debris. It's the fracture in the bedrock that was underneath all of that. And everything else has been eroded away. And we're looking at the fractured bedrock below it. So if it had been the original crater at the big extent of the rims, this would have been a lot bigger back then, right after the impact. You're just kind of looking at the center part of the bowl that cratered the rock. This is about 42 miles across, and these fractures extend for about another 30 miles or so. Huge. And you see the circular nature of that impact.
All right, so with these craters, like how big of a meteorite would you have to have that would take out like the world?
Yeah.
Maybe a couple million miles like this.
Like if we got hit with it, you're done.
Yeah, let's say we got hit by something the size of this room. It would take out pretty much southwestern Michigan. If we got hit by something the size of the building, you could probably kiss the United States goodbye. If you got hit by something the size of this campus, you could pretty much kiss Earth goodbye. Does that give you a few kind of
Yeah, it's kind of
rough
depressing, but
generality?
yeah, that's crazy.
And then if it hits a rush hour, oh my God.
I would think it would have to be bigger, like it doesn't.
We get bombarded all the time by meteorite debris. Little things about the size of BBs come in. We just kind of get a shower of that hourly. You know, it could bounce off your head and you just kind of go, huh, wonder what that was. You wouldn't even notice it. Most of the stuff burns up in the atmosphere. So we've probably got as good a chance of getting hit by space junk from the space program as we do of getting hit from a meteor. Okay, so I want to divide rocks into a couple of big categories, metamorphic. So we looked at regional metamorphism where it's directed pressure, right? We've got these big plates coming together. We're building the Himalaya mountains. So you know all the pressure is coming from just a couple directions head on. I'm going to get a type of metamorphic rock called a foliated rock. You can see the results of that directed pressure. The other type of rock is a non-foliated rock, pretty witty of geologists to go to that extent of detail. And here it's just general confining pressure. There's no directional, no direction that really outshines any other direction. All we get is the same from every direction, so we're not going to get any preferential alignment of minerals or any banding or any foliation. It's just going to be kind of the same, but we're going to cause some minerals to change. But we aren't going to see a lot of foliation. So what's foliation? Well, uniform pressure, if you think about it, confining pressure, if one direction's as good as another direction, they're all the same, there's nothing there to cause anything to line up in any specific order. So it's just going to put pressure on the system and cause minerals to change, but nothing is going to line up. But if I have a directed pressure where all the pressure, most of the pressure is coming from one direction along one axis, then things are going to start to line up in accordance with that pressure regime. And what we see is the maximum axis of stress here, we're going to see the minerals lining up at 90 degrees to that maximum stress direction. So they'll be lining up parallel to the minimum stress direction. If I squeeze stuff this way, the natural effect is it's going to kind of squeeze out at the ends this way, right? And the minerals are going to line up with that minimum stress direction in the process. And you can see here where we've got minerals that are all lined up pretty much left to right. And that would tell me that the maximum stress direction here goes from top to bottom. Squeezing it this way, having things line up this way. Look at this igneous salt and pepper diorite that we're starting with here. Pretty random orientation. Now I'm going to start to apply stress from the sides, squeeze it together, and look at how the darker mafic minerals band in and form 90 degrees to the direction of stress. Pretty cool. I've gone from an igneous rock here to a metamorphic rock here. So how does this process occur? Well, it's kind of hard to envision these solid grains within the rock just kind of twisting around and taking a new orientation. A little of that mechanical orientation does go on. But one of the big things that happens is we see mini fractures occur in these pebbles. Let's start with a round pebble like this, and I just start to mini fractures all through it. And little by little, a little slippage along each of them, and what used to be kind of a round rock now becomes an elongated one. So I would see that my pressure regime here is up and down, and it's causing the rock to realign left to right. That occurs, and it's pretty spectacular when we see it, but in general, that's not anything that happens. A lot of what we see is really ion migration. Okay, let's do this. True or false? Burial metamorphism is the principal cause of foliation. Okay. Okay, pretty good. Pretty much decided that was true. Okay. Well, what's burial metamorphism versus regional metamorphism? Those are the two types that cause or don't cause foliation. So, what direction does burial metamorphism produce pressure from?
All directions.
All directions, like this. Is that causing any foliation? No. In burial metamorphism, if I'm applying pressure from all sides, one side's as good as the other. Where's the principal stress axis to orient 90 degrees to? There isn't one. They're all the same. So what I need is some kind of metamorphism that's going to give me a major direction of stress. And that's going to be regional metamorphism, things like plate collisions, things like that. So the answer here, burial metamorphism being the principal cause of foliation, is very much false. Okay? So there's the connection you all need to kind of be thinking about. So, I get some deformation, I get some mini fracturing, microfracturing, and that kind of thing. The big thing is this ion migration. It's really chemical. And what I see is this rock, this sedimentary rock, and it's made up of grains. It's a detrital rock. And the grains are in contact with each other at, as you might guess, points of contact. And there are a few void spaces where the rock material is crusty. But these points of contact now are going to be high pressure areas. They're holding up the framework of the rock. And as the rock is buried, these points of contact are going to see higher and higher pressures. And as that happens, these are going to be localized spots now for chemical reactions. As that occurs, we're going to see, dissolution, chemical reactions occurring at these points of contact. And these ions now are going to start leaving these areas. It's kind of like in life in general, we're not too wild about high pressure situations, right? And we kind of head off to lower pressure situations. So, same thing with minerals and rocks. So these ions now are going to start migrating away from these contact points, these high pressure points, and they're going to go to the low pressure points. And where are those going to be? They're going to be these areas where the voids are. So these points of contact are going to erode away. These voids are going to get filled in. And look at the pattern that we end up with. Remember when we were looking at those big giant boulders, that spheroidal weathering pattern, and we saw First of all, we broke it up with mechanical cracks, then we attacked the outside and saw some chemical weathering. You know, kind of seeing the same thing here, aren't we? Points of contact, things are dissolving, it's getting closer, and the voids in between are filling in. Little by little by little, chemical ion migration. You can see that here. Here's a quartz sandstone. Nice round pebbles of quartz. Look at the inner growth going on between these grains right here. And eventually, I've metamorphosed this rock into what we call a quartzite. Just like a quartz sandstone, well, it becomes a quartzite. And look at the grains. No void spaces whatsoever. The grains are all just corroded and intergrown into each other. So we've seen this point-to-point contact and ion migration process run to the extreme. Okay. Remember how we talked about bedding planes with sedimentary rocks? How things are just kind of laid down in layers and given a chance to compact a little bit in between each new episode of sedimentation, we get a distinct plane between each layer, a bedding plane. And usually what we see is they're laid down pretty horizontally. Isn't that one of the first big rules of stratigraphy? Everything's laid down originally horizontal. But when I start building mountains, which way is the pressure being directed? Is it top to bottom? Or is it side to side as plates collide? Side to side. So with side-to-side collision, I would expect the grains in the metamorphic rocks to be oriented what? Horizontal or vertical? Vertical. 90 degrees to the pressure, right? Originally, my sedimentary rocks started out flat, horizontal. And they probably got a little boost with that as the basin filled in. And that was the loading pressure in the very beginning, but that changed as it was just confining pressure in general. And then I start this collision, and I start mountain building, and I change to where the principal stress axis is side to side coming together. And now the rock doesn't want to be layered horizontally. It wants to shift and become layered vertically in response to this new stress regime. Uh-oh, change is on the way. We got a metamorphosis. So little by little, what I see is what started out as flat horizontal bedding planes, ion migration starts to destroy those. It starts to go away. And in its place, I start to see cleavage planes that develop vertically in response to the stress. Things reorient. I'm not taking the bedding planes and flipping them up on end. Not at all. What I'm doing is I'm essentially destroying the old bedding planes, and I'm creating new cleavage planes that are now in tune with the stresses being applied from side to side, and those new cleavage planes developing vertically up and down. Now that sounds okay when I can be at the very end of the spectrum here saying, oh yeah, that's an obvious bedding plane, no sweat, sedimentary rock. Or it's okay when I'm up at this end of the metamorphic scale and I can see these cleavage planes and I can go, oh boy, those are nicely developed cleavage planes. But what happens when I'm kind of in between, in the middle of that spectrum of difference? Not quite so obvious sometimes. It can be a real bugger to figure out, am I dealing with sedimentary bedding planes that were originally horizontal, or am I looking at cleavage surfaces that are now vertical, created in response to the stress of the orogeny of the mountain building process? And a lot of times you can see a mixture of nicely developed cracks and cleavage planes with this faint kind of wispy bedding surface moving through it horizontally. You can see all sorts of styles